We're in the middle of a coronavirus pandemic, and the Centers for Disease Control has said that one of the most important things we can do during this time is to wash our hands for about 20 seconds. And to help us do this, they've recommended we sing happy birthday to ourselves. So, if you're going to sing happy birthday, you got to have birthday candles. So I have a candle here in front of me because I'm not going to tell you how old I really am. All right, but it makes me wonder a little bit. This candle's giving off heat and it's giving off light. But where does that heat and where does that light come from? As a chemistry teacher, I know that most of what a candle is paraffin wax, which is 20 carbon atoms and 42 hydrogen atoms all bonded together to form one long chain called a hydrocarbon. And I know that in an abundance of oxygen, like what we have in our atmosphere, that paraffin is being torn apart chemically and is forming 20 carbon dioxide atoms and 21 water molecules, and all these are going to be a gas and they become part of our atmosphere. So I can account for the mass of our reaction, but that still doesn't explain where the light and where the heat comes from. Well, the answer to that is found in something called thermochemistry. And so that's what we're going to talk about this week is thermochemistry. And then when it comes to thermochemistry, you got to understand that the bonds that hold atoms together represent energy that is stored. It's a form of potential energy called chemical potential energy. And those bonds, some bonds have a lot of energy and some bonds have a little bit of energy, but they all represent a certain amount of energy. And some chemical reactions release energy, and some chemical reactions absorb energy. Let me tell you what I mean. Okay, first of all chemical actions need at least a little bit of energy to get started. We call this the activation energy. Think of it as when you're on a roller coaster. It takes a little bit of energy to get up to the top of that first big hill. And then after that, it's kind of going basically on the energy that you saved up, and now you're using to go the rest of the way around the roller coaster. Well, chemical reactions have the same thing. They have this activation energy to get things started. And then after that, the energy that is involved. It depends on the energy that is involved in the bonds of these particular compounds. And every compound has its own special activation energy, and so we'll get into that later. Okay, so basically what happens is this. If the amount of energy that is stored in the starting molecule, what we call the reactants, is greater than the energy that is stored in the products, then that extra energy is going to be given off, oftentimes as heat. Well, we call these sorts of reactions exothermic reactions. And a good example of that is combustion. Once you get this candle burning, it will continue to burn until it's out of fuel or until I stop the reaction. Exothermic reactions are usually, in the case of the paraffin has a lot of energy stored between those hydrogen and those carbon atoms. But when those atoms get rearranged in the presence of oxygen, the amount of energy that is stored between the carbon and oxygen, or even hydrogen and oxygen, is less. So as a result, that extra energy that was once stored in the molecule as chemical potential energy is now being released as thermal energy. But in this case, it's also, in the case of combustion reactions, it's also given off as light. So we have two different kinds of energy that are given off. All right, and in a chemical reaction, what we do is when we write out that chemical reaction, if we're balancing the energy as well as the mass, then we'll put how many joules of energy, that's how energy is measured, that are released by this reaction. So if you ever see a chemical equation written where you have products and then you have reactants, and at the end of those reactants there's a number with a kJ beside it that stands for kilojoules, then that's an exothermic reaction. Examples of exothermic reaction include, of course, combustion, but also digesting your food. This is an exothermic reaction. It gives off energy. That's part of the energy that keeps us warm, keeps our body temperature up to a comfortable level. All right. Exothermic reactions tend to continue on until they either run out of reactants or something comes along to stop that reaction. For example, if I had not blown out the candle, it would still be burning right now because that exothermic reaction, that energy that is given off, is enough energy to start the next reaction. So you may start it with a few molecules, and then the energy that is released allows this next group of molecules to go, and then that energy is released allows the next molecules. And so they become kind of self-perpetuating, and they'll continue on until they run out of fuel or they run out of reactants. The opposite of an exothermic reaction is an endothermic reaction. Examples of endothermic reactions are things like photosynthesis, respiration, cooking. All of these are reactions that require energy in order to continue on. These are reactions that absorb energy from their environment. For example, let's take, for example, if any of you have ever been playing sports and you've injured yourself, and maybe the athletic trainer or the coach reaches into their first aid kit and they grab this pouch, right? This little plastic pouch. They squeeze it, they twist it, and they shake it up really fast, and they put it on your injury, and all of a sudden it feels ice cold. Well, what's happening? That's probably citric acetate in water, and what's happening is that's an endothermic reaction. When the acetate, that citric acetate reacts with water, it can't do it unless it absorbs lots of energy from its environment. So, put it on your arm, it absorbs all that energy from your arm or your leg or whatever you happen to hurt, all right, and it continues to draw that in. So we feel that as cold. It's the heat exiting our body. And so that cold that we feel, if we were to cut off that source of energy to that reaction would stop. And we see this, for example, in photosynthesis. Photosynthesis is an endothermic reaction. It doesn't require heat to continue on, but what it does require is energy in the form of light. And so what happens at night? Well, photosynthesis stops. Without the presence of that constant energy source, in this case the sun, that light from the sun to keep that reaction going, then the reaction stops. Same thing with cooking. Well, of course, we use that because I happen to like my steaks different than my wife or my mom or some of the people in my family. And so I like my steak a nice medium steak. My mom likes it a nice burnt, well done. And I know some people that like their steak rare. Well, fortunately for us, cooking is an endothermic reaction. There's a lot of things going on when we cook, all right, but we're changing a lot of the chemical reactions, a lot of the chemicals that are inside. We're breaking down amino acids, we're breaking down sugars, we're breaking down all these different things like this. But it requires a source of heat in order to do that. It requires us to cook it. So we put it on the pan and it starts to cook. Well, so when the food is cooked to the degree we want it to cook, we take it off of the heat. And what happens? Well, very quickly, without that constant source of energy coming in, the cooking process stops. Without that, we wouldn't be able to, for example, have medium rare steaks. All steaks would continue to cook until they were well done, or really, they passed that. They would cook until they were nothing more than a charcoal briquette. Because exothermic reactions tend to continue on until they run out of reactant, whereas endothermic reactions will continue until we cut off the energy source. So how do these look as a chemical reaction? Well, chemical equation. Well, just like exothermic reactions, we put where the heat is. We do the same thing, only this time the heat is listed as a reactant. It's on the reactant side. And so you may have the CO2 plus H2O plus, and maybe they'll have a triangle there. That triangle is the chemical physical energy symbol for heat. And so maybe they'll have a little triangle that says we have to add energy. Or maybe they'll have a number there because we know how much energy is required in order for us to make this reaction happen. So where does the energy go? Well, okay, yeah, no, I get it. It makes the energy, it makes the chemical reaction happen. But where does it go? It goes into the bonds that hold that particular product together. For example, photosynthesis. Photosynthesis is such an incredibly important reaction. What ends up happening is you take all this carbon dioxide, and again, the bonds between carbon and oxygen are not terribly energetic. And just like the bonds between oxygen and hydrogen aren't terribly energetic. So we add some energy to it in the form of light, and we get some enzymes going in there. And this is not a biochemistry class, so we're not going to go into too many details. All right, but when we're done, we end up with a glucose molecule. And that glucose molecule and a bunch of high oxygens that go float away and keep us all alive on our planet. All right, but that glucose molecule is now it's a hydrocarbon. It's a bunch of carbons and hydrogens and oxygens that are all bonded together. And those carbon to hydrogen bonds are more energetic than the carbon to oxygen bonds. And so as a result, what ends up happening is that energy that from the photosynthesis, that energy from the sun that we added to it, is now stored as the carbon bonds inside of our glucose molecule. So there you have it, thermochemistry. Kind of your two basic sides of thermal energy. The thermochemistry is exothermic, it gives off heat. They are self-perpetuating, they continue on until they're running out of reactants typically. All right, or endothermic. Endothermic reactions require energy throughout the entire reaction. And if we cut off that source of energy, the reactant very quickly stops. And what's happening again? All that energy, it's all stored in those chemical bonds between the atoms. So this week we're going to do a couple things with thermochemistry. We're going to look at how we balance those equations and how we recognize chemical and exothermic and endothermic reactions from looking at their equations. And until then, and until I see you on Zoom, stay safe and stay well.